Okay, this is Dr. Williamson, kind of doing a redo of the lecture last time, trying to summarize it a little bit better. I'll be writing with my mouse. The first law of thermodynamics says that the energy of the universe, the total energy of the universe, is a constant. Okay, and I can think of that as the energy of my system plus the energy of the surroundings. Okay, and what do I mean by the system? If I use my coffee cup calorimeter, right? This would be my system. Okay, I can't write. Remember, I'm using my mouse to write here. This would be my system. Right? An extra S there because you can't have too many S's. And then everything else would be my surroundings. Okay, so surroundings. The surroundings would surround it. If this is a constant, then the change in the energy of the universe would be 0 because it's constant. And that would be equal to the change in the energy of my system plus the change in the energy of the surroundings. Okay. So I could say then that the change in the energy of my system why we got to do the extra S, right? Is equal to minus change in the energy of the surroundings. Because if it's equal to 0, I bring this over to the other side of the equal sign. One of these two things gets the minus sign. I gave that one the minus sign. Okay. So I'll put the, oh, that's not what I wanted to do. Okay. Oh, come on. So then that means delta E system is equal to minus delta E surroundings. Whatever energy the system loses is exactly equal to the energy the surroundings gains, equal in numerical value, just opposite in sign. Okay. Also, any change in energy can be seen as equal to the heat plus work. Work is energy lost or gained due to force through distance or the organized motion of matter. Heat is not work. That's one way of putting it. So work is the transfer of energy across the system boundaries due to the organized motion of matter. Heat is not work, or an imprecise way of saying it is heat is the transfer of energy across the system boundaries due to a temperature difference. So I could say here that the heat plus work of the system is equal to the heat plus work of the surroundings. Now, in chemistry class, we're not going to be having too much work going on. We're not going to have any blocks on an inclined plane. We're not going to have any springs. We're not going to have any paddle wheels. We're not going to have any of that stuff. So we're going to know that any heat that the system loses is equal to the heat that the surroundings gains. And yeah, there's a minus sign on the surroundings, but the purpose of the minus sign is just to say whatever heat the system loses, the surroundings gains, they're equal in numerical value, opposite in mathematical sign. So if this was positive 50 calories, this will be negative 50 calories. And if this was negative 50 calories, this would be positive 50 calories or joules or whatever. Okay, so we got that. So I can replace this with, all right, see that I'll have to redo this. Okay. So I could rewrite it as Q system is equal to minus Q surroundings. Okay. Now, most of the time, I gotta check my phone. My phone kind of barked at me. All right. Heat. Where's my mouse? There's my mouse. Okay. Heat on a per mole basis under constant pressure conditions, meaning we perform the experiment with a loose lid. So any pressure built up is allowed to vent. Remember our coffee cup calorimeter had a sponge on top. Any pressure built up, that's given a special name. That's called enthalpy. The enthalpy of reaction. So I'm going to change this yet again to good night. That just will not stop doing that. Okay, so I'm going to change this to line. Okay. I'm going to change this to, I'll do it in green just to be different. I'm going to change this to the enthalpy of our system is equal to minus the enthalpy of the surroundings. All that means is the heat of the reaction in our experiment had a loose lid. Okay, and we did it on a per mole basis. That's all that means. Okay, so we got that. All right, now let me erase this stuff. For any spontaneous reaction, the entropy, the randomness change of the universe, for a reaction to be spontaneous, must be larger than 0, and that's equal to the entropy change of the system, whatever we're studying, plus the entropy of the surroundings. And an equation I'm going to drop down out of the sky on top of you is the entropy is equal to the heat of the reaction, in this case, chemical reaction, divided by the temperature. And if we do it under constant pressure conditions, it'll be the enthalpy over the temperature. Okay, so for a spontaneous reaction, man, what's going on here? All right, I'm making some space here, guys. So for a spontaneous reaction, delta H, or excuse me, the entropy of the universe is equal to the entropy of the system plus the entropy of the surroundings, right? That'll be equal to the entropy of the system plus delta H of the surroundings over the temperature. Okay, there's a reason for the math. There's a madness to the method, guys. There's a madness to the method. Okay. Well, remember, delta H of surroundings is equal delta S, delta H of the system with but a minus sign. I can move this minus sign to the other side. So I'm going to end up with here. This is equal to delta S of the system minus delta H of the system over the temperature. If I multiply everything through by minus T, I'm going to end up with minus T delta S of the universe is equal to delta H of the system minus T delta S of the system. Notice I now have everything in terms of the system, which I can easily measure. Like if I have my coffee cup calorimeter, I could measure what's going on inside of here. Measuring the surroundings is really hard because I got to put a thermometer everywhere in the lab room. Okay, we talked about that. So I can use that equation. I'm going to rename this now. I'm going to call minus T delta S. I'm going to call that delta G. So now I'm going to have delta G is equal to delta H minus T delta S. And in your appendix, you have tabulated values of this Gibbs free energy. You have tabulated values of enthalpy. You guys remember doing that in Chem 1A. You have tabulated values of entropy. And you can calculate these. And if delta G is less than 0, then the chemical reaction you're looking at or studying, the chemical reaction is spontaneous. And the number of joules you calculate from delta G is the amount of free energy you get out of it. If delta G is greater than 0, then the reaction is non-spontaneous, and the value of delta G you get for that is the amount of energy you have to put into the reaction to force it to go. And if you guys kind of remember from the lecture I gave with the coupled chemical reactors that the chemical engineer was looking at, I could use the Gibbs free energy from this spontaneous reaction to perhaps drive another chemical reaction that was of value to me or my patients or my clients or whatever. Okay. And all of this was allowed me to calculate how much energy I can get out of a reaction for free by studying only the reaction and not having to also know everything about the surroundings. That's just the way nature works. So we'll talk about that more later, but I hope that helps, guys. Okay. All right, then. Let me see if I can stop recording this.